Now after studying about the electric flux, now let's move on to the theorem which is associated with the electric flux, and this theorem is called the Gauss Theorem. Now in order to understand what is this Gauss Theorem or Gauss Law, first you have to understand the electric flux linked with the closed surface. In this condition, first we have to understand what is this closed surface. If I talk about the closed surface, so in this condition I am talking about the 3D figure. Like for example sphere. Sphere is considered as a closed surface. In the other hand, the circle is considered as an open surface. Similarly, cuboid. The cuboid is considered as a closed surface, while the square or a rectangle is considered as the open surface. So, a closed surface is a surface which has a volume and which is represented in a 3 dimension. Like for example, if I show you what is a closed surface, in this condition, this is the box. Okay, you can see this box. This box has a particular volume. So this box represents the closed surface. Now we are talking about the closed surface in the case of Gauss theorem. Till now we have studied the electric flux in the case of open surface. Like for example a parallelogram, which can be a square, which can be a rhombus. But here we are dealing with the volume surface, which is called a closed surface. Now you can look at this figure. This is the figure. You can look, there are 6 surfaces. Okay, this 1, 2, 3, 4, 5 and 6. So these are the 6 surfaces of this closed surface. Now let's talk about this figure. Now in this condition, let me draw a closed surface, that is, let's say a cuboid. So this cuboid is also a closed surface which has 6 sides. Okay, now in this condition, if this cuboid is placed in an electric field, if this is the electric field in which this closed surface is placed, and you have to find the total flux in this condition. So what is the flux in this condition? In this condition, the flux which is given by the formula integral E dot ds. This formula we have already studied about it. But if we talk of the closed surface, so in that condition this integration changed to this particular symbol. This symbol, that is a circle on top of the integration, it represents a closed surface. Now you can see from the formula that the flux is found of the closed surface, which is shown by this particular symbol. Now I already told you that the surface, that is a closed surface, has 6 sides. Okay, 1, 2, 3, 4, 5 and the back one, that is 6. It has 6 sides. If we expand this formula, then it gives you the value, that is flux is equals to, for surface 1 it becomes E dot ds, for surface 2 it again becomes E dot ds, and it goes on and on till it reaches surface 6, that is E dot ds. So this particular formula, when it is expanded, then for every surface it gives you the distinct value of integration. And what is integration? Integration is adding of all individual values. That's why if we summarize this formula, so you will get one formula, which is this. This formula shows that the value is taken within a closed surface because sign is there, and all values are added up, like we are adding all the surfaces. So this is all about the closed surface. Now let's consider the 2 points. Okay, in the first point the charge is placed outside the closed surface, and in the second point the charge is placed inside the closed surface. Now let's first start when the charge is placed outside the closed surface at any point but outside this cuboid. In this condition, this cuboid is subjected to the electric field. These are the electric field that are directed towards the cuboid. Okay, these are the electric field. This is how the electric field are directed towards the cuboid, because the charge is placed outside the cuboid. Now you have to consider all the surfaces one by one. If I talk about this surface, the surface, which is the first one. Okay, in this condition you can see that the electric field is going in this direction, but the area vector of this particular surface is outward because it is perpendicular. So the area vector is in this direction. This is the area vector. Now the electric field intensity is in this direction. This is the direction, and area field vector is in this direction. So what is the theta between the two? The theta in this condition is 180 degree. So according to the formula, that is E dot A cos theta. Cos theta is 180 degree. Cos 180 degree give you minus 1. So it becomes minus of E dot A. So for the first surface, this is the first surface, the front one, the flux is minus E dot A. Similarly, you have to solve for all the surfaces. Now let's consider this cuboid. This is similar to that of the cuboid. These are the electric lines of forces which are directed towards the cuboid. You can see here, these are the electric lines of forces directed. Okay, this is how it is directed, and the area vector of this surface is directed outward because area vector is always perpendicular to the surface. So the direction the area vector is outward and the electric line is going inward. So the angle between this and this, that is area vector and the electric field intensity, is 180 degrees. So it becomes minus of EA. Similarly, you have to solve for the portion which is at the back side. Okay, this is the portion on the back side. In this way, we can show it. If the electric lines of forces are going in this direction, so it is coming out of this particular surface. This is how the electric lines are coming out of this surface. What is the area vector? The area vector is perpendicular to the plane. So this is the direction of the area vector. What is the angle between the two? The angle between the two is 0 degree. So cos 0 degree is 1. So this side your flux is E dot A. So you can write here at the back portion of it, that is the second portion, the flux is coming E dot A. Similarly, solve for other sides also. Now let us consider this side. Okay, this side we are considering, the electric field is coming in this direction. Okay, and the area vector is perpendicular to the plane. What is the angle between the two? The angle between the electric field and the area vector is 90 degree, and cos 90 degree is 0. So in that condition, the flux is also 0. Similarly, solve for this also. In this condition also, the flux is 0. Similarly, solve for this condition also. The electric line is coming in this direction. The area vector is perpendicular to the plane. So what is the angle between the two? 90 degrees. So in this condition also, the flux is 0. Similarly, solve for this direction also. Now you can see here, again the flux is 0 because the angle between the area vector and the electric line is again 90 degree. So now you can see from here, on calculating the total flux, if we have to calculate the total flux over all the 6 surfaces, so our answer is plus E dot A of the second surface. Next is your minus of E dot A of the first surface, and all surfaces are coming 0. Okay, because we have already calculated that 4 surfaces are giving you the flux, that is 0. When you add all these quantities, so your answer is 0. So I have proved here that when the charge is placed outside the closed surface, in that condition the total flux linked with the surface is 0. So now we are not going to consider the charge which is placed outside the closed surface. You can even understand this particular very small example. Now let's suppose this is open at all ends. If I project water from one end, then what happened? This water which I project at this side all flows from this side. Any water collects inside this box? No, because whatever the water is projected by one end is projected out from another end. So no water retains inside this closed surface. That represents the quantity of water inside the closed surface is 0. And this is what we have proved, that the flux inside the closed surface is 0. Now in the second condition, if I place a charge inside this closed surface, then what will happen? Now my charge is there inside the closed surface. Okay. Now this charge which is inside the box projects the electric field outward. So this is how it projects the electric field outward, like this. Okay. It is going in all these directions. Now you can consider all the surfaces one by one. In this condition, when the electric field is coming out, if I consider this first surface, this is the one surface. In this condition, the electric field is coming out from inside. It is coming out. Okay. What is the direction of the area vector? The area vector is also coming out. This is the direction of the area vector, and the electric field is also coming out. What is the angle between the two? The angle between the two is 0 degree. So the flux along the first surface is coming E dot A. Now let's again understand by the sample piece. Okay. This is again a cuboid. I put the charge inside this box. Okay, inside the box I put the charge, and this charge is enclosed. Now the charge projects the electric field outward. If I consider this surface, then what is the direction of the electric field? The direction of the electric field is coming out. From inside it is coming out. This is the direction. And what is the direction of the area vector? The area vector is also coming out, that is perpendicular to the plane. So what are the direction between these two vectors? These two vectors have the direction between them 0 degree. So this is how it is 0 degree, and it is coming E dot A. Similarly, this side, if you consider, in this condition also the electric field is coming out because the charge is inside. So the electric field vector is coming out. Where is area vector? The area vector is again out of the plane, that is perpendicular to the plane. What is the angle between the two? The angle between the two is 0 degree. Again for second surface also the flux is E dot A. Similarly, if I consider this surface, upper surface, in this condition also you see the electric field is coming out because the charge is inside. The area vector is perpendicular to the plane. What is the angle between the two? Again 0 degree. Your answer is E dot A. Consider this side. This side also the electric field vector is coming out, and the area vector is perpendicular to the plane. What is the angle between the two? It is again 0 degree. That is, at all sides, at all 6 sides of the cuboid, you will get the same answer, that is the angle between E and A is 0 degree. And what is the flux in that condition? The flux is E dot A. Now for every surfaces you get the flux, that is E dot A. If I consider this one, if I consider this one, for all 6 you will get E dot A. Now if I ask you to find the total flux in this condition, so what is the total flux in this condition? The total flux is, you have to add E dot A 6 times. So answer is 6 into E dot A. So now you can compare the two cases, that when the flux is calculated by keeping the charge outside the closed surface is 0, and now when the flux is calculated when the charge is kept inside the closed surface having some magnitude. So this is called a Gauss law. Okay. Now according to this Gauss law, the Gauss has said that whenever any charge is placed inside the closed surface, then the total flux is given by 1 by epsilon naught times the total value of the charge enclosed within the surface. This is the statement of the law. Now let me demonstrate you clearly. In this condition, okay, I talk of, let's say, one charge, and in this condition the charge, let's say, produce 100 lines, 100 electric field lines. If I talk about two charges, then it produce 200 lines. If I talk about, let's say, 3 charges, then it produce 300 lines. But the Gauss have worked upon it, and he told us that it does not produce 100, 200, 300, 1000. No, actually it produces 1 by epsilon naught electric field lines. So according to his statement, he told us that 1 coulomb of charge, if produce 1 by epsilon naught times the electric field lines, so Q coulomb of charge produces Q upon epsilon naught times the electric field lines. So now if we formulate the law, so it told us that the flux calculated by keeping the charge inside the closed sphere is equals to Q upon epsilon naught. So this is the formula and this is called the Gauss law. Now if I expand this formula, then how it is written as? It is also written as that flux is equals to, we have given a formula that a closed surface E dot ds, this is the integration done along the electric field intensity and the ds over the closed surface. This is E also equals to Q upon epsilon naught. So this is all about the Gauss theorem. Now after studying about the Gauss law, let's see some important points related to the Gauss law. The first very important point is that the charge is always considered inside the closed surface. About this point we have already discussed upon it, that is when the charge is placed outside then the total flux is 0. When the charge is placed inside, only in that condition the Gauss law is applicable. Now let's see the second condition. In this condition, if there are multiple charges which are placed inside the closed sphere, for example if I talk about, let's say this is any closed body, okay. Now if in that condition there are multiple charges, let's say plus Q, minus 2Q, plus 3Q and so on. So in order to find the Gauss law, that is the total flux, in that condition all the charges are considered. That is, you have to consider plus Q, minus 2Q, plus 3Q. That is, it becomes 2Q. So the total flux is related to summation of all the charges. So the next important point is that you have to consider the multiple charges which are placed inside the closed surface. Now the third important point is, if suppose there are some charges outside the body and some charges inside the body, so in that condition what is the total flux? Now if suppose again this is a closed surface, some charges are inside the body while let's say some charges are outside the body, okay. So now by this plus 2Q and plus 3Q the electric flux is created, but the net flux is only considered by the plus Q charge, that is the charge which is placed inside the body. Now you can see here this is plus 2Q, okay. It produces the electric field and this electric field goes outward. As soon as it entered, it goes out and it moves out. So there is no electric flux retains here. Similarly, if I talk about plus 3Q, it produces the electric field outward and it enters inside and then again it moves outward, okay. And suppose it produces more electric field, it again moves outward. No electric flux is retained inside this closed surface. Now if I consider plus Q charge, okay, this is a plus Q charge, this produces the electric field, then this produces the electric field outward like this, okay. Now you can see here it produces the electric field out of the plane. There are no negative polarity to cancel this electric field. So in this condition the electric flux is there inside the closed surface. So the net electric flux is only given by the charge which is there inside the closed surface. So here the third point comes, that when the charges are inside and outside, then the net flux is given only by the inside charge. Next, the fourth point is that you have to consider the Gauss law only for the Gaussian surface, okay. That is, the Gauss law is considered for the Gaussian surface. What is this Gaussian surface? The Gaussian is a 3D surface with a particular volume. Like for example, it can be a cuboid, it can be a cylinder, it can be a sphere and so on. So the Gauss's law is only applicable for these particular kind of surfaces. Next comes the fifth point. The fifth is a very important point. I am specially highlighting it because this point states that the Gauss law only exists if there is a inverse square law property of the Coulomb's law. That is, it is dependent upon the inverse square law. This inverse square law, okay, I am talking about this inverse square law. This inverse square law, if it would be there in the Coulomb's law, then only you found the Gauss law. Now you will say, what is this inverse square law? According to this law, we have proven that E is inversely proportional to R square. So you can see from here that E is inversely proportional to R square. So this law becomes a inverse square law. And if this law won't be there, so Gauss law also won't be there. So this law is very important for you to derive the Gauss law, which is flux is equals to Q upon epsilon naught. So this condition we will study in the next part, that is how to prove the Gauss law. From there I can prove that why this inverse square law is so important for us to make the Gauss law. Now we told that this is the Gauss law, but still we hadn't proved that how this law came into existence. In this particular notes, you are going to study that how the Gauss law is proved. Now let us consider a charge that is plus Q. This charge is placed inside a Gaussian surface. We have taken the Gaussian surface as a sphere, okay. This is the sphere in which the plus Q charge is placed at the center of the sphere. Now as it is plus in nature, so the electric field is directed outward. So this is how the electric field of this plus Q charge is directed outward. This is the electric field, okay. Now let us consider a very small portion of the sphere. If suppose I consider this small portion of the sphere, then this portion of the sphere has a very small area, and this area let us represent by ds, okay. Now this ds has an area vector which is perpendicular to the plane of the ds, and this area vector is also directed outward. The direction of the area vector is also outward, and the unit vector is given by a with a cap on it. Now you can see here that the electric field intensity is also coming in this direction, and the area vector is also coming in this direction. So what is the angle between the two? The angle between A and E, theta, is equals to 0 degree. So we have to find the total electric flux over this whole closed surface. Now let's start with it. In this condition, we know that what is the formula for electric field intensity? The formula for electric field intensity is 1 by 4 pi epsilon naught Q upon R square. All the formula remains the same, and one thing is still missing in this diagram, that the distance of the Q to this point, that is the radius of the sphere, is given to you R. So all these points are R. So in this condition, this separation distance is represented as the radius, because we are considering the distance of Q to that of the area, that is ds. Now if the electric field intensity is given by this small formula, so we know what is the formula for the electric flux. The electric flux is given by E dot A dot cos of theta. Here we are considering a very small area, so in this condition the flux is also very small, so it becomes d phi is equals to E dot A cos of theta. Now just look very carefully in this condition, the area now becomes in this condition E dot ds dot cos of theta, okay. What is the angle between the E and the area? The angle between them is 0 degree, so it becomes d phi is equals to E dot ds. Now E we already have seen from equation 1, you can put the value directly here, that is d phi, it becomes 1 by 4 pi epsilon naught Q upon R square dot ds. Putting this value directly into d phi. Now just look very carefully, this d phi, that is the flux, is a very small flux which is considered along the ds. ds is a very small area, so along it the flux which we have calculated is d phi. If we have to find the total flux, okay, the total flux over the closed sphere. So in that condition, if this is d phi. So if we find the flux here, so it also becomes d phi. If we find the flux here, it also becomes d phi and d phi here. On adding all these value d phi, d phi, d phi, you will get the total flux over the sphere. So in that condition, we don't need to add all the values. We just use one particular system which we call integration. So this formula modifies into phi is equals to integration 1 by 4 pi epsilon naught q upon r square dot ds, and this integration is done over a closed surface. That's why the sign is made like this. Now if we modify this formula, then it becomes phi is equals to 1 by 4 pi epsilon naught q upon r square. Okay, this is q. Integration over the surface is done of ds. What is this ds? ds is a very small area of the sphere. If the integration of this ds is done, that means we are talking about ds, 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 ds. All ds should add it up to get the total surface area. And what is the formula for total surface area of the sphere? The formula for it, 4 pi r square. So this integration of ds, which is a very small area, is given by the formula that is 4 pi r square. Put this formula directly here. You will get 1 by 4 pi epsilon naught q upon r square into 4 pi r square. Now cancel out the values. You will get here flux is equals to q upon epsilon naught. So this is the Gauss law, and this is all we need to prove. Now look at this equation, how this equation comes. This equation only comes when this electric field intensity is proportional to r square. You can see here that when we put the formula for electric field intensity, that is 1 by 4 pi epsilon naught q upon r square, this E is proportional to r square as an inverse sign. So it is called inverse square law. If this won't be applicable, then r square does not get cancelled out, and you are not getting the Gauss law. That means the inverse square law is very important for you to get the Gauss law. So this is the fifth property that I told you to discuss later on. Similarly, you can see here, if this is the electric field intensity, okay, and I modify it, this formula can also be written as the closed integration E dot ds. It can be also written like this. Now, from this formula, you can see this electric field intensity is here, the Q is also here. Okay, if I remove the electric field intensity, then the Q is also removed. That means this E is supporting Q. E is incomplete without the Q. This is called the Maxwell's first equation, which you will study later on. It gives us the relationship between E and Q, and it also tells us that it comes from the Gauss law. So from this equation, you can see here that E is dependent upon the Q, which is called the Maxwell's first equation.